Hello everyone, welcome back to our third session on embedded systems. We were discussing the fifth module in embedded systems. So far we have discussed about process, threads, and we started with task. So we have discussed what are task and what is the concept behind multitasking and multiprocessing, the difference. That's where we stopped in the previous session. So in the previous session, we ended with discussing multitasking. There we defined the terms context switching, context saving, and context retrieval. Today, we shall continue with task. So, in this session, we shall cover the different types of multitasking and the different types of scheduling algorithms. And we shall also give a brief intro to inter-process communication. So let's begin. So what are the types of multitasking? So we have seen that multitasking involves keeping ready all the processes into the memory and switching the CPU from executing one task to another, right? So while doing so, how do we switch the CPU from one task to another? The different ways of switching the CPU gives us the different types of multitasking. The oldest form of multitasking is the cooperative multitasking. See here, what happens is a task, or a process, whatever. A task or a process gets a chance to execute only once the currently executing process voluntarily releases the CPU. Say I have task 1 and task 2. Task 1 is currently running and next to be executed is task 2. Task 2 can only start execution once the task 1, the currently executing task, the task 1 voluntarily releases the CPU. Yes? So, in this method what happens is, this task 1 can hold the CPU for as much time as it wants. And if task 2 want to start executing, the current task, task 1, must be willing to leave the CPU. See, so task 2 depends upon the mercy of task 1 to get the CPU back. And hence the name cooperative multitasking. See, the task 2 is requesting the cooperation for task 1 to get back the CPU, right? Hence the name cooperative multitasking. So what is cooperative multitasking? A task can only execute if the currently running task releases the CPU voluntarily. So there must be a cooperation between these tasks so that all the tasks can execute. If the current task, say my task 1 is non-cooperative, what happens? The other task will have to wait for a very long time to get the CPU back. Okay, so this is one type of multitasking called the cooperative multitasking. Okay, the second type of multitasking is preemptive multitasking. So preemptive multitasking, let's start guessing from the name. Preemptive, empty, to get completed, right? Empty. Preemptive, before getting completed. Before. So before getting empty or before getting completed itself, there is multitasking. So what happens in preemptive type of multitasking is, suppose task 1 is executing. Task 1 starts executing. After some time, task 1 is blocked. Then task 2 starts executing. And task 2 executes for a certain time and again task 2 gets blocked. and the third task, task 3 is executed. After certain time, again we come back to task 1, then task 2, task 3. So in this type of multitasking, every task, every process gets a chance to execute, right? So when and how much time is required for each task depends upon the scheduling algorithm that we are going to use. So the thing is, before a task completes itself, another task will get a chance for execution, right? Hence the name preemptive. Before a task gets emptied itself, the next task can execute, right? So this is called preemptive multitasking. So in this kind, the currently running task is preempted. This is very important, is preempted to give a chance for the other task to execute. And this preemption of task, it may be based on the time slots. As I have said, suppose I am executing task 1 for 10 minutes. After 10 minutes, I switch to task 2. Again after 10 minutes, I switch to task 3 for 10 minutes, coming back to task 1. So it may be on a fixed time slot, or else it may be based on priorities. Among these 3 tasks, suppose task 1 has the highest priority. So I'll first execute task 1 for say 5 minutes. The second priority comes for task 3. So after executing task 1 for 5 minutes, I shall go and execute task 3 for 5 minutes and then task 2. So this preemption may be either based on time slots or even based on the process priorities. Okay, so I hope these 2 types of multitasking is clear. Then the third type, if we have preemption, we will have no non-preemption. So the third type is non-preemptive multitasking. So here what happens is, a process or a task which is currently running will execute until it terminates, or it enter the blocked or wait state. So suppose task 1 is executing, task 1 will continue execution until it completes, or until it enter the block state or waiting state. Is that clear? Yeah. So in cooperative multitasking, only once task 1 voluntarily, willingly gives the CPU to the other task can execute. So they need a cooperation between the tasks, right? Preemptive multitasking. Here every task gets a chance to execute. Even before one task completes its execution, another task gets the chance. So that may be based on time slots or even priorities. And in non-preemptive multitasking, the process which is currently using the CPU can execute until it terminates or enters the blocked state. Now, in fact, this non-preemptive and the cooperative may seem similar, right? Because both can use the CPU until it terminates, right? Then what is the difference between them? So the difference arises in their behavior once the task enters the blocked state. If it is non-preemptive multitasking, once task 1 has just entered the blocked state, the CPU will be immediately given to the task 2 or task 3, whatever, right? In non-preemptive, if task 1 enters a blocked state, at the same instant the CPU is given to task 2 or task 3. They doesn't require the permission for task 1 to approve of the CPU release. But that is not in the case of cooperative multitasking. In cooperative multitasking, your process or your task need not always voluntarily give the CPU when it enters the blocked or wait state. In cooperative multitasking, even if your task 1 enters the blocked state, it is still the wish of your task whether it need to release the CPU or not. That was not in the case of non-preemptive multitasking. Yes. So I hope the different types of multitasking, cooperative, just so you can just identify these 3 types from the names itself. Cooperative, waiting for task, currently running task to complete and give the CPU to the other task. So it's very it requires the mercy or the cooperation of the currently running task. Second type was preemptive. Before here every process gets a chance for execution. Before being emptied, another task can execute. Non-preemptive is the right opposite. A currently running task can release the CPU only once it completes or it enters its terminated state, or once it enters their blocked or wait state. So I hope these 3 types of multitasking is clear. Next we shall move on to the task scheduling. Okay. So see, we have been discussing about multitasking. We have 3 tasks: task A, task B, task C. Now, which task to select first? Which task to be executed second? Which task to be executed third? Actually, we need a policy to determine how to select the task and how to assign each task the CPU. This process of determining which task to be executed at a particular point is known as task or process scheduling, right? So task scheduling, in fact, that is the basis of multitasking, because task scheduling gives us an idea of determining what task to be selected when, right? And the kernel service or the kernel application which implements this scheduling algorithm is called as the scheduler. So while we are scheduling the task for execution, we must be aware of the states in which the task is switching, which is the ready state, the running, the blocked, the completed state. So we have different states of execution, right? So the scheduler must have an idea of these states, along which the scheduler must also consider the following factors, which are the CPU utilization. See, our scheduling algorithm should always make sure that the CPU utilization is high. When is the CPU utilization high? When your CPU is always busy or always executing, your CPU utilization is high. And this is in fact a measure of your system's efficiency. So it gives us a knowledge about how well the CPU is being utilized. So the scheduler or the scheduling algorithm must make use of the CPU utilization. Along with that, throughput. See, the throughput or this gives us an idea about the number of processes which are being executed per unit time. And of course, the throughput of a good scheduler should always be high, right? Which indicates that a huge number of processes are being executed at a particular time. So this in fact shows the efficiency of the scheduler and hence your system. The third factor is the turnaround time. In fact, see, turn around to complete. So this is the time taken by the process to complete its execution. So see, this includes all the time, the process in its wait time, in its ready queue, in its execution time, in its operation, everything together comes under the turnaround time. So it's a total time from in its created, ready, running, blocked, all this time together taken by a process to completes its execution. And another factor is the waiting time. Just as the name indicates, it's the amount of time the process spent in its ready queue, or it's the amount of time the process waits to be executed by the CPU. And what must be this time? The waiting time must be minimum, so that each process is being executed very fast, right? Now, and the last factor is the response time. So this is some kind of a delay, or I can define this as the time between the submission of a process or the start of an execution and its first response or its first output. The difference between start of an execution and its first response is called the response time. And again, what must be the ideal value for this? For a good scheduler or for a good scheduling algorithm, the response time must be very small, which means the instant I give my process for execution, I must get a output response. So the delay, in fact, the delay must be minimum. So while we select a scheduling algorithm, we must take into consideration all these factors. So why you need a scheduler, what is a scheduler, what is scheduling, and the factors to be determined, I hope these things are clear. Now, just as we had different types of multitasking, we have different types of scheduling. Basically two types: the non-preemptive scheduling and the preemptive scheduling. See, this is very similar to the non-preemptive and preemptive multitasking. So in non-preemptive scheduling, see, we basically implement this type where non-preemptive multitasking is used. This is very obvious, right? If your system uses non-preemptive multitasking, the scheduling we use will be non-preemptive, right? In this type of scheduling, what we do is the process or task which is currently being executed is made to run or made to execute until it terminates or enters their wait state. It's clear, right? Just as we have said in the case of multitasking model. So the currently executed process continues its execution till they terminate or enters the wait state. That is non-preemptive scheduling. We have different types of non-preemptive scheduling, like the first come first served. Just like standing in a queue, right? If you come first, you will be first served. The other kind is the right opposite. The last come first served. Perhaps maybe submitting your notebooks, right? You pile one above the other, and the teacher may correct, not always, okay, in most cases the teacher may correct the first notebook on the top which has arrived last. So you can consider it that way, the last come first served. Another type is the shortest job first. So you have three tasks. First task requires say 2 minutes. Second task requires 5 minutes. Third task requires 1 minute. So the shortest job first means the third task will be done first, which has 1 minute of execution. Then the first task, which has 2 minutes. And then the third task, which has 5 minutes. So that is the shortest job first type of scheduling. And the last kind is priority based scheduling, of course based on priority. The highest priority job may be first considered, then the second highest priority, and so on. So based on these criteria, we have different types of scheduling: first in first out, last in first out, shortest job, and the priority based scheduling. All these are types of non-preemptive scheduling model, right? The other kind of scheduling is the preemptive scheduling, just like the multitasking kind. So again we implement or prefer the preemptive scheduling where preemptive multitasking model is used, just like the non-preemptive thing. So in this kind of scheduling, all the tasks that we have to perform is in the ready queue. All the tasks, say all my tasks 1, 2 and 3 are in the ready queue, and all these tasks will get a chance to execute. How and when do they get the chance to execute depends upon our algorithm. So here in this kind of scheduling, our scheduler can temporarily stop a currently executing task and select another task from your queue. Suppose I have task 1, 2, 3 and in my queue. Task 1 is being executed. After 5 minutes, say my scheduler decide to stop my task 1, and then it will consider another task in my queue. It may be second task or the third task, depends upon my scheduler, right? Okay. So here again we have different types of preemptive scheduling. Again the preemptive, shortest job first, preemptive kind of shortest job. Then the round robin scheduling and the priority based scheduling. So here all these names, right, preemptive shortest remaining time and priority based, these are similar except that their nature is preemptive. Round robin, this is a preemptive scheduling in which we fix the time interval. Say just I have said in the case of preemptive multitasking, we have fixed time slots for which your task executes, say 10 seconds. So for 10 seconds task 1 will execute. At the end of 10 seconds, your task 1 is in the wait state. Then task 2 for the next 10 seconds. Then task 3, and this continues. So that is the round robin scheduling, and it's one of the most easiest way to schedule preemptive task. So that's it. So regarding task, we have seen what is task, how is it related to a process, the task control blocks, what is multitasking, types of multitasking, and the types of scheduling. So far we have seen what is process, thread and task. These three are so interrelated yet different. So what are those? We have seen that. In the next set of videos, we shall discuss about inter-process communication. So here I am just going to give a very brief idea about what is inter-process communication and what shall we be discussing in the coming units or coming sessions. So see, just from the name itself we can guess, right? Inter-process communication. Communication between different processes, that's called inter-process communication. So what are the situations in which we use inter-process communication? If you want to interrupt a present process for another process, we must tell another process that currently executing process that another process want to execute, which means there must be a communication between these processes. In that case, you need IPC or inter-process communication. If you want to notify an event of another waiting process, again you need IPC. If you want to give a set to reset signal, if you want to generate information about other sets or computations, in all these cases we need IPC. Now, how can you facilitate this inter-process communication? We have different tools. I have to say different tools. Signals, semaphore, message passing, message queues, mailbox, pipes, socket, memory mapped files, shared memory, RPC, remote procedure call. These are different methods by which we can make inter-process communication possible. So in the next sessions, we shall see each of these in detail. So that's for this session. For any doubt, let me know, and please go through your notes also. Thank you.